All right, so for the main content today, I'm going to start chapter 4. We'll just work through a bunch of problems about using calculus to graph functions, first of all, using first and second derivatives, and ultimately using calculus to solve optimization problems. As we go through this chapter 4 here, I'm also going to be having you read the very last section of chapter 3. It's kind of a theoretical section about theorems from calculus, the most prominent of which is called the mean value theorem. And I will bring those theorems into the discussion as we go, as we work on solving the problems in chapter 4. If you got your book, you can open it to section 4.1. Just going to try to work through as many problems as we can in these lectures. These class periods, I should say. They're not really not lectures so much. Again, the focus is on using calculus, first and second derivatives, to help us graph, trying to avoid technology as much as possible. Learn how to use the calculus to avoid technology as much as possible. There are definitely benefits to that. Though I also won't hesitate to use the technology, in particular Mathematica, whenever it seems appropriate, or my calculator. So let's go ahead and start with looking at these problems here, numbers 4 through 8. I won't do all of them. I'll just pick a couple of them. Say we take a look at number 6 here. This is section 4.1, number 6. Okay. When I go through these problems, I may or may not assign the same problems I do together with you as homework. Sometimes I might, sometimes I might not. Okay. But they will all help you do the homework. The directions say to use derivatives to find the critical points and inflection points of the given function. In number 6, you can see the function is f of x equals x to the 5th plus 15x to the 4th plus 25. Well, we haven't said what critical points and inflection points are a ton, at least. I think I have mentioned them, but you may not remember it. Critical points of a function are where its derivative equals 0 or where its derivative is undefined. A critical point of f is a value of x, a number x, where f prime of x equals 0 or f prime of x is undefined. Though with most examples, it'll consist of those places where f prime of x equals 0. Why would we care about finding places where f prime of x is equal to 0 or undefined? Focus on where it's 0. Think about it. Think about what we've learned so far. Derivatives tell you where a function is increasing and decreasing, right? When the derivative is positive, that tells you the function is increasing if it's positive over some interval. And where the derivative is negative, that tells where the function is decreasing. Where is it going to change from positive to negative? Where it's 0. It's kind of like the velocity problem with the ball going up in the air and then coming back down. There's some instant in time where it reaches the peak, where the instantaneous rate of change, the velocity, is 0. That's kind of what we're doing here, except we're not necessarily thinking of it as physics. So what do you have to do? You've got to find the derivative and solve for where it's undefined or 0. In this case, since the function is a polynomial, it's always going to be defined. This is differentiable everywhere. So we'll only look for where it's 0. By the way, try your best to be in math mode here, in the math zone, right? Pretty much every word I say is important. So really, really do your best to pay attention. F prime of x, what is that? Well, that's a pretty easy derivative problem, right? You're used to this kind of thing. 5x to the fourth plus 60x cubed plus 0. Please do double check my work. I make plenty of mistakes. I'll be the first to admit it. So hopefully I'm trying my best to avoid mistakes, but if you think you see one, let me know. That is the derivative. Where does it equal 0? Well, certainly it would be 0 when x is 0. Is there any other place where it's 0? Try to factor it as much as possible. Do you remember when we were talking about taking derivatives at first? Trying to prep for the gateway, I said you didn't have to simplify your answer. And in particular, with a problem like this, you wouldn't have to factor it. However, I also said it's useful to factor derivatives whenever you can. These two terms do have a common factor of x cubed. They also have a common factor of 5. I can factor out of 5x cubed. I'm reversing the distributive property here. What's left over inside? Well, there's an x there and a, well, 12 right there, right? Because 5 times 12 is 60. That's the derivative in factored form. Set this equal to 0. That word's supposed to say set. Set this equal to 0 and solve for x. Solve for its roots. It's zeros. Sometimes that's hard to do. Here it's fairly easy. The only way a product like this can be 0 is if one of the factors is 0. This implies either x cubed equals 0 or x plus 12 equals 0. But the only way x cubed can be 0 is if x itself is 0. And x plus 12 will be 0 when x is negative 12. These are your only two critical points. These are your two critical points. They are the places where the derivative equals 0. And those are the only two ways to get 0. And since this function is differentiable everywhere, it's got a derivative everywhere for all x. The derivative is never undefined. I don't have to worry about that. It's not asked in the problem, but let me use the derivative and these critical points to help me figure out something about the graph of f. Something, well, what thing? Let me use these derivatives, the derivative and these critical points, to help me figure out where the graph of f is increasing and decreasing. Typical way people show this work is they draw a number line and they write their critical points on the number line. They mark them, in this case, negative 12 and 0. Those two spots are where the derivative equals 0. In between these three intervals that these two numbers break the number line into, the derivative is either going to be positive or negative. And it's continuous. It's got to change sign, S-I-G-N, at those critical points from positive to negative or negative to positive. Sometimes it actually doesn't change sign at critical points, and that might happen here, but let's see what happens. So you want to test the sign S-I-G-N of f prime in each interval. Essentially, we're making a little chart here with a number line. Plug in some number in each of these subintervals here. Plug in a number less than negative 12, like negative 13. Or at least imagine plugging it in. You actually don't have to actually plug it in. Just imagine plugging in. Plug in x equals negative 13 up into the derivative in the factored form. Negative 13 cubed is some huge negative number. Important thing is that it's negative. Times positive 5 is still negative. Negative 13 plus 12 is negative 1. Positive times negative is positive. The derivative is positive here. You might want to make a little note to yourself that I imagine plugging in negative 13 to help me figure that out. I could plug in negative 14, negative 15, negative 13.73. It doesn't matter. Plug in anything less than negative 12. I get a positive times a negative is positive. Now plug in something between negative 12 and 0, like negative 6. Or just imagine plugging in. Negative 6 cubed is negative. 3 factors that are all negative gives you a negative. Times positive 5 is still negative, but then negative 6 plus 12 is positive. Positive 6. Positive times positive is negative. The sign of f prime is negative between negative 12 and 0. Now plug in a number bigger than 0, like, hey, how about 1? I would get positive times positive times positive. The derivative is positive over there. This tells me information about f. I could call it the direction of f. Direction of f, meaning is it increasing or decreasing? The derivative is positive over the interval from minus infinity to negative 12, so f is increasing. Going upward, abbreviate that increasing by INCR, when x is less than negative 12. The derivative is negative between negative 12 and 0. So f is decreasing. Draw a downward pointing arrow. Not straight down, but down to the right, because we're trying to also emphasize as x is increasing. And when x is bigger than 0, the derivative is positive, f is increasing. So the graph of f, which I'm not drawing yet, has to go up, then down, then back up. If you didn't have technology, this would be pretty much the only way you can figure this kind of stuff out. Now with technology, you can get off easy and just have the technology do it for you, though one way this analysis is still useful is that it can help you pick the right window for the technology. Like if you pick a bad window for this function and graph it, like we'll try a bad window, like from negative 5 to 5, you won't see all these features. You need to go at least from like negative 14 to positive 2 or something, at least, to make sure you include all these features. What about inflection points? What are inflection points? Inflection points are the places where the concavity changes. Concave up to concave down, or concave down to concave up. Concave up, it looks like part of a smile. Concave down, the graph looks like part of a frown. We've got to look for where the second derivative is 0. Those are going to be possible inflection points. Are they always inflection points? Technically not, actually, but usually they are. Do critical points always give you local maxes like tops of hilltops and local mins like bottoms of valleys? Not always. Usually they do, but not always, actually. We'll look at some special cases as we go here. But we're trying now to find inflection points. Inflection points, or an inflection point, of f is a value of x where technically you don't say f double prime of x is 0 or doesn't exist. We actually emphasize the concavity changes, where the concavity changes from either concave up to concave down or vice versa as x increases. This is all as x increases. As x increases. So we need to find the second derivative. There's the first derivative. The second derivative of f is the derivative of the first derivative. So I need to differentiate that. Differentiate 5x to the fourth gives you 20x cubed. Differentiate 60x cubed gives you 180x squared. Question? You could. It's probably easier to do this one though. No, they're not that much different. Either way is okay. So again, differentiate that, you get 20x cubed. And you differentiate 5x to the fourth. Differentiate 60x cubed, you get 180x squared. It's good to try to factor this. This got a common factor of 20x squared in both terms. (180) is 20 times 9. Once again, set this equal to 0. Set this equal to 0 and solve for x. X squared is 0 or x plus 9 is 0, which means x itself is 0 or x is negative 9. Are these guaranteed inflection points? Actually not. The second derivative truly does have to change sign at these for them to be true inflection points. Let's see what happens. You can make another number line, marking off these candidates for inflection points, negative 9 and 0, testing the sign of f double prime. Imagine plugging in first a number less than negative 9, like negative 10. Negative 10 squared is positive, times 20 is still positive, but negative 10 plus 9 is negative. Positive times negative is negative. The sign of f double prime is negative when x is less than negative 9. When x is between negative 9 and 0, like negative 4 or negative 5, for example, you plug in x equals negative 4 here, you get 20 times negative 4 squared is still positive. Negative 4 plus 9 is positive. Positive times positive is positive. The sign of f double prime is positive there. It does not change back to negative as we increase through 0 because of the square there. You plug in a positive number, like 1, you get positive times positive still. The second derivative is 0 at x equals 0. However, f double prime does not change sign from positive to negative as x increases through 0. You might wonder what's happening then. How can that be? We'll try to see if we can see it in the graph. What does this tell you about f? It tells you not the direction of f, like the sign of f prime told you, but instead you might say the concavity of f. Whether it's like part of a smile or part of a frown. When it's part of a frown, that means it's concave down, and it's nice that those rhyme. Frown, concave down. Right, nice that those rhyme. Not necessarily a full frown, though I will draw a full frown. It could be just a partial frown, and in fact, it will be here. Actually, no, it will be more of a full frown. Bigger on one side than the other. Where it's positive, make smiles. Concave up. So I found the critical points, 0, negative 12, and I found the only inflection point is actually 0, not negative, negative 9, not 0. I meant to circle negative 9. Negative 9 is actually the only inflection point, even though the second derivative is 0 at 0. That's the only inflection point. Because the second derivative doesn't change sign at 0. Question?
Yeah, so when you find the critical points, are those always guaranteed to be critical points? Or are they like?
They are always guaranteed to be critical points here, but they're not always guaranteed to be where you have what's called a local max or a local min.
Okay.
So the question with the inflection point's a bit different. It's not just where the second derivative equals 0. You have to actually change sign of the second derivative. Very subtle point to make sure you're really paying attention to. Let's try to now use this information to draw a rough sketch of the graph of f without technology. It's not asked for the problem, but let's give it a shot. Evidently, very important points include -12, -9, and 0 for x. Are some important places for x to think about. How can I draw this without technology? You got to think about these directions as well as these concavities kind of all at once. You got to be really careful. It's also worth noting that the y-intercept of this function is 25. F of 0 is 25. That's worth noting. Let's pretend this is 25. So there's your y-intercept. 25. Let me go higher here. Another thing worth noting is that this has no linear term in it. And because of that, the slope at the y-intercept is 0. Actually, we already knew that because we know 0 is a critical point. Okay, so let's start to draw it here. It's got to go, look at this picture here. It's got to go up and up and up and then reach a local maximum when x is -12. How high will it have to be when x is -12? It'll have to be above 25 because it's going to be coming down to 25 as x goes between -12 and 0. So I got to be way up here somewhere, probably off the paper. It's going to be probably way up there. I don't know how much further, but let's just draw it up there. You're going to be increasing when x is less than -12, heading up to -12, where you will have a high point, what's called a local maximum. Because look at this picture again. F is going to be increasing when x is less than -12 and decreasing shortly after -12. So -12 has to be a high point when x is -12. I don't know exactly how high it goes here. I could figure it out. Maybe I should by plugging -12 into the function. F of -12 is -12 to the 5th plus 15 times -12 to the 4th plus 25. -12 to the 5th is that. Wow, big negative number. Plus 15 times -12 -12 to the 4th, which is going to be a big positive number. Oh, okay. I added it to that. So the 62,208 is not what 15 times -12 to the 4th is. It's what that plus the previous answer is. And then plus 25. Yeah, it's way off the scale. The second coordinate of this point is 62,233. This picture is way wrong to scale. Okay. The coordinates of that point are -12, 62,233. Bad picture here, okay, but humor me. Just pretend it's way up off the paper. Then it's got to come down and it's got to have an inflection point at -9 where the concavity changes. It's been concave down. You see it looks like a frown, which really means the slope is decreasing. Large positive slope to small positive slope to zero slope to negative slope to large negative slope. There's an inflection point at -9, after which it looks like part of a smile. And in fact, so it's decreasing between -12 and 0. After 0, it's got to go back up again. And in fact, it's concave up the whole way once x is past -9, but that concavity gets somehow close to 0 when x is equal to 0. And I'll just say that what that means is that effectively the graph, even though it's concave up over here and concave up over here, it's relatively flat near zero. Where is the x-intercept over here? I don't know, but it's less than -12. So the graph looks something like this, though what the scale is way off. But we did answer the question. We did find the critical points, 0, -12. We did find the inflection point, -9, not 0, because the second derivative did not change sign. Typically, where f double prime is 0, the second derivative will change sign. It just didn't happen in this example. And that definitely made it worth doing. You got to be careful. Yeah, I mean, as far as plotting this thing in Mathematica goes, or your calculator for that matter, you got to pick a good window, right? If you pick a bad window, like for example, so here we have, I'll just plug the function in like this. Well, let me define the function first. F of x equals x to the 5th plus 15x to the 4th plus 25. If I plot it in a sort of an ordinary looking window, and maybe let Mathematica pick the plot range for me, I'm not really getting a full picture of the graph. I am sort of seeing that it's flat near 0, but I'm not seeing the part over here when x is less than -12 where it's increasing. I need a bigger window, maybe -14 to 5. Now I'm seeing the graph more fully, but even that's not as good as it could be. Try going up to say 7 now. That's a little bit better, maybe 10, and maybe -6, 17 or something. Okay, there I'm seeing a better picture of the graph. And yeah, on this scale, you can see near 0, the graph is relatively flat, you might say. It's definitely concave up when x is bigger than -9 over here and less than 0, and concave up over here when x is bigger than 0. It's so flat, so to speak, near 0 that the concavity at 0, you might say, is 0. And that makes 0 not an inflection point because the concavity doesn't change. By the way, if you pick a plot range in the vertical direction, say, 0 to 100 or something, it won't look quite as flat near 0 as this graph shows. You can see it's going up and down pretty rapidly over here, but when you get really close to 0, it looks pretty flat. The difference in how these things look is dependent on the scale. So let Mathematica pick the plot range, it looks like that. You pick a plot range like 0 to 100, it looks like that. It looks different, but it really is still the same function. The scales are affecting your view of it. And even with the technology, then, what I'm trying to emphasize is the calculus calculations can still help you understand what's going on and help you understand why you're seeing different things at different scales in this example. All right, on to the next problem. Please stop me if you've got a question as we go. You've done a good job so far. Well, hopefully I didn't just break my calculator. Right? Oh, I did just break the pen, my red pen. It's a danger when the tables are not right next to each other. Let's look at now this problem. Number 8. F of x equals 4x times e to the 3x. Do the same thing, find the critical points, find the inflection points. 4x times e to the 3x. Not a polynomial anymore. This is number 8. F of x equals 4x times e to the 3x. But the directions are the same. Find the critical points, find the inflection points. I will also try to figure out where f is increasing and decreasing, concave up and concave down, and try to graph it. Do notice that it's got a y-intercept at 0. f of 0 equals 0. And in fact, that's also an x-intercept. I scratched that out because it just didn't look very good. F of 0 does equal 0, right? Because 4 times 0 is 0. Either the 0 is 1, but that doesn't matter because you got an x there. What's the derivative? What rules do I need? Product rule and chain rule. I've got a first function and a second function. The derivative of the first function is 4 times the second function plus the first function times the derivative of the second, the derivative of e to the 3x is e to the 3x times 3. That's good enough for a gateway problem. But for using calculus, it's good to try to factor. We can factor out a 4. We can also factor out a common factor of e to the 3x, which is really nice because e to the 3x is never 0. And in fact, it's always positive. By the way, that would be true even if it was e to the negative 3x, it would still be positive. E to any power, any real number power is positive. What's left over inside? It's this. Set that equal to 0 and solve for x. E to the 3x, again, is never 0 for all x. So this implies that only 1 plus 3x is 0, and therefore 3x is negative 1, and therefore x is negative 1/3. That is a critical point of f. Whether or not f changes sign as x increases through negative 1/3, we haven't tested yet. Let's go ahead and test it. Make your number line. Draw your critical points. In this case, there's only one of them. Look at the sign of f prime in each interval by testing numbers. And again, you imagine plugging numbers into the derivative here. You can literally plug them in if you want, but you don't always have to. You can just think, when I plug in a number less than negative 1/3, like negative 1, is this quantity going to be positive or negative? That's positive. That's positive. E to the negative 3 is a positive number. But this, when x is negative 1, is negative. It would be negative 2 when x is negative 1. Positive times negative is negative. Sign of f prime is negative. When x is bigger than negative 1/3, like 0, for example, what's the sign of f prime? Positive times positive times positive. Positive. So the direction of f is downward over here, decreasing, and upward over here, increasing. Does that mean the graph of f looks like a parabola? Not necessarily. You have to think about the long-term behavior of the graph as well. It might be parabola-like near negative 1/3, but not exactly. It can't be exactly. This is not a quadratic function. So one critical point, there's your answer for the critical point. What about inflection points? I got to find the second derivative, f double prime of x. Is it easier to use this formula or this one? They're fairly similar level of difficulty. This time, let's try it with this one. Let's use the product rule. Got a first function here and a second function there. The derivative of the first function, 4e to the 3x, is 12e to the 3x times the second function plus the first function times the derivative of the second, and the derivative of 1 plus 3x is 3. I used the product rule that time on the factored form. I also could have differentiated the unfactored form. Either way you do it, you want to factor this. There's a common factor, once again, of 4e to the 3x in both terms. What are you left with? With this term, you're left with a 3 from the 12, because 4 times 3 is 12. You're also left with the 1 plus 3x in parentheses. Parentheses must be there. It's going to be wrong. You're going to make a mistake if they're not. And with this term, there's only a 3 left over. Simplify. 3 plus 3 is 6. We get a 9x plus 6. 9x because 3 times 3 is 9. If I want, I can also factor out a 3 out of this. I could write this as 12e to the 3x times 3x plus 1. Hopefully I didn't make a mistake. I'm seeing something kind of interesting here. And perhaps unexpected, unless I made a mistake. Yeah, okay, 3x plus 2, thank you. All right, that makes a little bit more comforting. I was going to say the inflection point's occurring at the critical point if this was a 3x plus 1, which can happen, but is not typical. Set this equal to 0 to solve for possible inflection points. Draw a number line again. Mark off your possible inflection points. This is never 0, so this means 3x plus 2 must be 0, so that means 3x is -2, or x is -2/3, is a possible inflection point. -2/3. Is it an actual inflection point? What's the sign of f double prime? Does f double prime really change sign as x increases through -2/3? In this case, it does. If you plug in a number less than -2/3, like -1, positive, positive, negative, right? If you plug in x equals -1, there you'll get -3 plus 2 is -1. Positive times negative is negative. Plug in a number bigger than -2/3 here, you'll get positive times positive times positive. For example, if x is 0, this is 2. F double prime is positive. So the concavity of f is concave down here, concave up over there. And that does mean, since it changes concavity, that this is an inflection point. By the way, sometimes people use the word critical point and an inflection point for the x values that we're talking about here. Like you see, sometimes they actually mean the point in the graph for those x values, which is actually more common for the inflection points. I'm okay either way. If you want to just identify the x values, or if you want to find also the y coordinates of the point in the graph and call those critical points and inflection points. You should be able to find them if I ask you to find them. All right, let's combine this information, perhaps as well as some other information to help us graph this function without technology. Again, the function is 4x e to the 3x. Important points include -2/3, -1/3, and 0 was also important because that was where the y-intercept was. And in fact, the y-intercept is at 0. The graph goes to the origin here. And by the way, there are no other x-intercepts because there's no other way for this function to equal 0 except when x itself equals 0. Before I think about these numbers, let's think about when x is positive. You plug in positive numbers into this thing, you'll get a positive output. And in fact, 4x and especially e to the 3x are growing very fast as x increases and is positive. This graph over here is going to increase very rapidly. It's linear growth times exponential growth. That exponential growth is enough to make the graph go up very rapidly. What about when x is negative? You've got a critical point at negative 1/3 that is going to be what we call a local minimum because the graph goes down over here, then back up over here. There's got to be a local minimum at negative 1/3, a valley, you might say, a low point. There's no other x-intercepts. The graph cannot cross the x-axis again. There's an inflection point at negative 2/3 where the concavity changes. Sorry, this is getting messy because I should have put my number labels in above the axis instead of below. There's an inflection point about here. And because there's no other x-intercepts, and more importantly, because this function does go to 0 as x goes to minus infinity, you're going to have a horizontal asymptote. The limit of this function as x goes to minus infinity is in fact 0. That's a 3x there. In spite of the fact that 4 times a number getting very big negatively becomes a very big negative number. The reason this is 0 is because e to the positive 3x, let me rewrite this. E to the positive 3x gets very, very, very close to 0 very, very rapidly as x gets more big negatively. Like when x is negative 10, that's an e to the negative 30 power. What's e to the negative 30 power? In scientific notation, it's about 9 times 10 to the negative 14. Very, very close to 0. You multiply it times 4 times 10, or 4 times negative 10, times negative 40, it's still tiny. On the order of 10 to the negative 12. It's going to be very close to the horizontal axis. The y coordinates are very close to 0. This is 0. The graph has a horizontal asymptote as x, at y equals 0 as x goes to minus infinity. An inflection point here, that's an inflection point. This is negative 2/3 here. A minimum here at negative 1/3. Both an x and a y intercept here at the origin and goes up very rapidly as x goes to plus infinity. I didn't mean to make a big dot there. That's a rough sketch of the graph. Check it with Mathematica. Four x times e to the 3x. You need to use a capital E. Plot it. Let's let Mathematica pick a plot range first. Oh, I bet since I'm going up to 10 here, I bet it's going to be going very high. So I'm going to want to modify this. Yeah, look at that, 10 to the 8th. Oh, how about negative 5 to 2? Let's try that. It still goes up pretty high. How about negative 5 to 1? There we're seeing it a little bit better. I can modify the plot range here. Negative 1 to 1, say, just to see how it affects things. Maybe change this to a negative 3. Based on what I did here by hand, it helps me decide on the window. In minimum at negative 1/3 right there, that says x is negative 1/3. Inflection point at x equals negative 2/3, right about there. It's concave down over here, looks like part of a frown, until you get to a point right about there where it changes to a smile. Let's end class with one more example. Let's take a look at number 22 in section 4.1. This one right here. If A is a non-zero constant, find all critical points of this function of x. And also use the second derivative test, which I haven't mentioned yet, what that is, to show that if A is positive, then the graph has a local minimum, and if A is negative, the graph has a local maximum. If there's a second derivative test, is there also a first derivative test? Yes, there are. I think I will also do a first derivative test here. So again, this is number 22. F of x equals, the formula is a over x squared plus x, which you can also write as a times x to the negative 2 power plus x. And that'll be a little bit more convenient for finding the derivative. We can avoid the quotient rule, although the quotient rule is not that difficult to use here. Maybe, since I've got this unspecified parameter a in there, maybe I should call this function f sub a. And in fact, I'm going to, and I will do this kind of thing a lot. It's going to be a very, very helpful thing to label a function name with a subscript where the subscript represents an unspecified constant. You might call it a parameter. And then what we're ultimately really interested in here is what happens as that parameter changes. That'll be helpful, really helpful for these applied problems that we'll be doing based on these worksheets. Again, don't forget after class ends here to come up and pick these up. I'll try to remind you again. And how do the answers depend on A? That might be interesting to know, and then perhaps important for applications. Find all critical points. So I've got to find the derivative. With respect to x, x is the variable, a is the constant. But keep the a in there. When you write it this way, you don't have to use the quotient rule. You can bring down that negative 2, subtract 1 from the exponent. And there's the derivative, and then derivative of x is plus 1. Though, if you're going to set this equal to 0 and solve for x, then it might be better to write this as a fraction. Not that you have to, it might be helpful. Like that. X to the negative 3 power is the same as 1 over x to the positive 3. How do you solve for x here? You can think of it a couple ways. One way is you could add this expression to both sides to get 1 equals 2a over x cubed. And then the only way this is going to be 1 is if 2a equals x cubed, which you can think of in terms of cross multiplication as well, if you prefer. Multiply both sides by x cubed, effectively. X cubed must be 2a, and so x must be the cube root of 2a. And that will be positive, a positive critical point, if a itself is positive, and a negative critical point if a itself is negative. That might be worth realizing. It is a critical point. It is a spot where the derivative is 0. Are there any spots where the derivative is undefined? Actually, there is. When x is 0, it's undefined. However, should we really call that a critical point because the original function is also undefined at x equals 0? Maybe we shouldn't. If the original function is not even defined there, it's just a place where the original function is undefined. Maybe there's a vertical asymptote for its graph at x equals 0. And that actually is the case. Tracking with me here? Talking about stuff you've thought about in the past. But, you know, trying to apply all your knowledge fairly quickly here. Loudon? I added it to both sides of the equation, so it became positive. Added it to both sides to cancel on the left side and get a positive 2a over x cubed over there. Let's consider the case where a is positive. And when a is positive, I think we'll think about this also maybe, well, okay. Let's go ahead and mark 0 on here as well. That's where f is undefined. F and f prime are undefined. And if a is positive, the cube root of 2a is over here to the right somewhere, say right here. In the case where a is positive. What is the sign of f prime? Imagine plugging numbers into f prime. Think with me here. A is positive. Think carefully. If I plug in a negative number for x here, like -1, -1 cubed is -1. It's still negative. 2a over -1, if a is positive, is negative. But then the negative of that is its opposite. It would become positive. And a positive number plus 1 is still positive. F prime is positive over there. Tracking with me? I imagine plugging -1 into here. Positive divided by negative is negative, but then a negative sign there gives me positive. Positive plus positive is positive. When x is in here, well, maybe we should ignore x being in there. Let's imagine x is really big. How big? Oh, I don't know what a is, so I don't know exactly what to say. Just imagine it's really big. If I plug in a really big number for x, a big positive number, x cubed is a really big positive number, and -2a divided by a really big positive number is a small negative number. Negative and close to 0 is what I mean. Plus 1, if this is small enough at least, will be positive. If this is like -0.1 plus 1, that would be positive 0.9. F prime is positive over here. Is it negative in here? Yes, it is. If you imagine a is fairly large and you plug in a small positive number for x, like 0.1, say, 0.1 cubed is really close to 0, like 0.1 cubed would be 0.001. Negative number divided by a very small positive number is a large negative number. Plus 1 is going to be negative. F prime is negative in here. That's tricky kinds of reasoning, but it is valid. So f is increasing over here, decreasing in here, increasing over here, and undefined at 0. It's going to be a vertical asymptote at 0, it turns out. Shouldn't be so surprising when you look at its formula there. And in fact, this point is going to be a minimum, because you can see the functions decreasing before that point and then increasing after. There's going to be what's called a local minimum at this point. That's actually the essence of the first derivative test, which is not part of the directions. The directions don't say to use the first derivative test. You're going to read about it. F prime is changing sign from negative to positive at this critical point. That means the graph is looking like a smile. I bet F double prime at this point is positive. And that will be true, and that'll be the essence of the second derivative test. Let's find the second derivative now. Take the derivative of this. A is constant. Differentiate that part, you'd bring the -3 down in front, right? Tracking with me? Bring the -3 down. -3 times -2 is +6. I get +6a, x to the -4. Subtract 1 from that exponent. Derivative of 1 is 0. Hey, that's a fairly simple function. And this function, this second derivative, is never 0. The only way a fraction can be 0 is if the numerator is 0. But 6a is a non-zero constant. In fact, it's a positive constant here when we're in this case where a is positive. And this is always positive, no matter what x is. This exists and is positive as long as x is non-zero. So the graph of f, except for the place where it's undefined, f prime and f double prime are undefined at 0. The sign of f double prime is always positive when a is positive, so the graph of f is always concave up. F double prime is positive in both spots. F itself is concave up in both spots. And that's like what I hinted at would happen over here. The graph near x equals cube root of 2a is going to look like a smile, and it will have a low point at this critical point because it changes from decreasing to increasing. Another way to think of it is the graph looks like part of a smile. So what does the graph of f look like here? It's got a vertical asymptote at 0. It actually has a slant asymptote as well, because as x goes to plus or minus infinity, this part goes to 0, and the whole function approaches x, a straight line with a slope of 1 to the origin. So I can fairly quickly draw the graph of this in the case where a is positive by first maybe drawing a dashed line for y equals x. It's tricky here. Let's see. It's increasing and concave up over here. Hang with me here. This is important. We might also wonder whether this has any other x-intercepts. If I set this equal to 0 and solve for x, does it have any x-intercepts? We could do that by rewriting that equation like that. Then we can cross multiply and say this. And then multiply both sides by -1 to get this. It does have an x-intercept at cube root of -a. Now, we don't know what a is, but we are assuming it's positive. That's going to be a negative number. There is an x-intercept over here somewhere. Let me just quickly draw what the graph is going to look like. It's going to look about like that when x is negative. And it's going to look like a smile over here. I'm unsure whether it's going to... Actually, it's not going to cross that line, I'm pretty sure. Okay, it's going to look something like this over here. And this point is going to be at cube root of 2a. And this point is at cube root of -a, which I should have drawn closer to the origin here. Scratch that out. This is going to be cube root of -a. That's going to be about what the graph looks like in the case where a is positive, and you will have a minimum here. Now, that's a pretty complicated kind of thing to do that I just did there. And we are out of time. I would suggest rethinking about this yourself, maybe rewatching the video from today, this last 15, 20 minutes here. It's really important to me that you understand this, because this is the heart of what makes this kind of stuff most useful. And it will help us with our applied problems, with our quote unquote projects. Okay? So give it some more effort. See you on Monday.